All right, so before we go ahead and think about solving those equations, we just need to do a quick review of how we solve ordinary differential equations in general. This is just a quick review of calculus that you probably should have seen before at some point, but just to jog your memory, we're just going to take a look at first order systems first, and if our ordinary differential equation has this form, it has a general solution which can be written as the sum of what's called a complementary function, which is the solution to the homogeneous equation, which is this thing set to 0, and the particular solution. So the complementary function, as I say, is just the solution of this part set to 0, and that has a general form as a constant multiplied by exponential function to the negative at. So we're looking at basically showing the dynamics of this particular system, how y changes with respect to t, and then once we've found the complementary function, we need to then find the particular solution, and for a steady state condition we just say that's the initial condition, dy by dt is equal to 0, and then solve this equation when dy by dt equals 0. So obviously that's just given by b over a, and therefore we can put both of those two pieces together, the complementary function plus the particular solution, to get this general solution down here. So how does that work in practice? Well, if we take a look at just a simple example, we're given this equation here to start with, 2 times the derivative of x with respect to t plus 3x equals 6. The first thing we need to do to that is to basically get this derivative on its own here on the left hand side. So we're going to divide through by 2 to get this. And now I can find my complementary function and my particular solution based on this equation. As we've said, complementary function has this general format here. So what we can do, if our solution x of t is given by this, we can differentiate that. Remember, we bring down the power of the exponential function, but the power doesn't change. So if we now have an expression for x and an expression for dx by dt, we can plug it back into this equation up here, which is what we're doing here. So I have the derivative plus 3 over 2 multiplied by x, which is this, equals 0 for the homogeneous solution, right? And therefore I can divide through by a e to the minus at to just get this, and therefore I've solved for my constant a. And then, as we said before, the particular solution is given just by b over a, right? So 3 over 2 just gives me 2. So the general solution of this differential equation is the complementary function plus the particular solution. So this thing here, complementary function with general form plus the particular solution, a equals 2. So to find the value of this constant capital A here, we can just apply an initial condition. If we have one that's different to everything equaling 0 at time t equals 0, then we can apply that here. And of course, if t equals 0 in here, this whole thing goes to 1, so we're just left with a plus 2 is equal to 0. So capital A is equal to negative 2. So we put all of that together, and we find our solution to that ordinary differential equation. Now, based on this solution, we can make some key observations about the behavior of that dynamic system. So first of all, if we look at the constant a, which in this case is 3 over 2, right? If a is greater than 0, then this power is negative, which means that x, as t increases, exhibits exponential decay, in which case it is stable, right? If, however, a is negative, then this power becomes positive, and as t increases, x exhibits exponential growth, which is of course unstable. And if a is equal to 0, then this whole power is 0, this whole expression here goes to 1, and so as t increases, x remains constant, and therefore we have what's called neutral stability. One other thing that characterizes our dynamical system is something called the time constant, and this is the time it takes for x to reach 63.2% of its final value. We choose this value here because, of course, the time it takes for x to reach its final value always tends to infinity, so we pick some intermediate step, right? And the time constant is given by the expression tau, 1 over a. So in our case, 1 over 3 over 2 is 2 over 3. And if that value is greater than 0, then of course the dynamical system is stable. So now let's just extend that and have a quick look at second order systems. Alright, so for second order systems, we're going to consider the typical example, which hopefully most of you have seen before, which is the spring mass damper system. We have a number of different forces acting within this system. Of course, we have the mass of the mass, right, multiplied by the acceleration. We have the spring constant. We have the damper constant, and we have all of those forces acting on our spring mass damper system. So the equation which characterizes that system is given by this second order ordinary differential equation here. So we're going to call that double star because we're going to come back to that. But basically the technique for solving this is to look at what happens when we try to find the roots of the characteristic equation. So here I'm calling x squared, I'm calling x the derivative of small x with respect to t, x squared the second derivative of small x with respect to t, and so on. So my characteristic equation is basically this quadratic here. And I can find, or I can analyze what happens with the roots of that quadratic equation by looking at the quadratic formula, right? So some special things happen depending on the size or the sign of what's going on in here. So different things happen when 4mk is larger than c squared, 4mk is equal to c squared, and 4mk is less than c squared. So we consider those three different possibilities, right? So let's take the first case. If c squared is larger than 4mk, that means that this expression in the square root here is greater than 0, which means we get two real roots out of that quadratic formula. So we call those P1 and P2. They're not equal to each other, and therefore we find one version of the general solution to this original equation up here as this thing, which is similar to the general solution to the first order system that we just seen an example of, right? But this time we have two constants multiplying this exponential function with our real roots up here in the power of e multiplied by t. And of course we can see the same types of behavior as we saw before, depending on whether these powers up here in the exponential function are greater than, equal to, or less than 0, right? So all of that is fairly straightforward. I hope you've seen that stuff before. So now the second type of possibility that we can have based on this quadratic formula here is if 4mk is actually equal to c squared, and therefore this square root is 0, and we end up with only one real root. And if we end up with only one real root, obviously p, so one real root, it's actually two real roots that are equal to each other, right? But that gives us a general solution to that original second order differential equation given by this, where we just have a t now appearing in this second portion of the expression here. And again, we can analyze the behavior of that solution based on the sign of the power of the exponential function. Now, we get on to what happens when we have a negative value inside of this square root over here. Now, obviously, we're going to start dealing with complex numbers now because the square root of -1 is an imaginary number, right? We call it I. And what happens if 4mk is larger than c squared, we end up with a solution to that quadratic formula that's given by two sets of complex conjugate roots, okay? So this is called complex conjugate pair, P1, A plus BI, and P2 is A minus BI. And therefore our general solution to our original equation is given by this expression up here. And the sign of the real part, whether it's greater than, equal to, or less than 0, so the real part here is A, tells us about the stability and the behavior of that dynamical system. So A characterizes the stability, and B here, which is the imaginary part, characterizes the frequency of that solution. So that allows us again to define some characteristics of that spring mass damper system by basically rearranging the original equation up here. So you remember we had these coefficients m, c, and k. Well, I'm going to rewrite this by dividing through by m, and that will characterize some certain characteristics about the spring mass damper system, right? So that's all I've done here is divided through by capital M. And then I've defined what we're going to call the natural frequency, omega n, as the square root of this part. Now all of this will become apparent in a moment, but you'll see why these are written in the way that they are. So the natural frequency, omega n, is going to be given by the square root of km, which is the square root of this part here. The damping ratio, zeta, is given by c over 2 multiplied by the square root of km. And then we have the product of this and this giving us what we call the exponential frequency, and WD, which is the damping frequency, is given by omega n multiplied by this square root here. And that allows us, putting all of that stuff together, to rewrite this equation up here in a slightly different form now, where we have the characteristics of that solution showing up directly in the equation, right? So just by looking at this, we can make some conclusions about what the frequency is, what the damping ratio is, and so on, right? So this is a much more this way of writing the equation tells us much more information than it does in this form, right? Because we can read off directly some of these characteristics. So if we rewrite our equation in this form, the complex conjugate pair roots of the characteristic equation now appear slightly differently, like this, right? Again, where the solution tells us something about the equation characteristics, the damping, the natural frequency, and so on. So again, it's just a neat way of rewriting the solution so that the solution immediately tells us something about the dynamics, right? And then again, we can define the time constant and the period, capital T. So what happens is we put all of that together is we can actually plot in the real versus imaginary axes, these solutions, the complex conjugate pairs. And the solution will look something like this. So we plot the real part of the complex conjugate pair along the x-axis and the imaginary part of the complex conjugate pair on the y-axis. So over here you can see we have a solution that's got a negative real part and then we have the plus or minus the complex conjugates over here in this plane, where again, reading off this chart, we can work out what the natural frequency is, the damping ratio, and so on. And if we're in polar coordinates, we can find the length of this this line here. We call it r, just using a bit of Pythagoras' theorem, right? The square root of the square of this length plus the square root of that length, and that gives us the natural frequency. And also we can find the damping ratio simply by considering the angle that line makes with the real axis. So this is how we go ahead and basically characterize solutions of dynamical systems if we are left in the situation where we have these complex conjugate roots, and we're going to need to use this in order to analyze solutions of our own dynamical system, which obviously characterize the dynamics of our aeroplane. So one final thing to point out here about when we go ahead and plot our complex conjugate pairs is that depending on where these solutions sit within these planes over here, tells us something about how the solution behaves. So if you take a look at this chart over here, you can see the real axis determines, as we've said before, how stable or unstable the solution is. So obviously at when A, the real part, is equal to 0, that's neutrally stable. So this picture corresponds to this solution, this picture corresponds to this solution, and so on, right? So if the real part is equal to 0, obviously we have some neutral stability. If the real part becomes less than 0, we have a stable system. If the real part is greater than 0, we have an unstable system. And then basically the magnitude of the complex part, B, determines how fast or slow the frequency is. So for a low value of B, we have a lower frequency than a higher value of B. So just to give you an example, if we have a large value of A and also a large value of B, then we have something that's stable but has a high frequency. If we have a positive value of A and also a, well, let's say a small value of B, we have something that's unstable and has low frequency. So depending on where the solution lies in this imaginary versus real chart over here, tells us how the solution of that dynamical system behaves.